Hi, I'm Metta Spencer, and today let's go on to the high seas and investigate what can be done to save the climate on our planet by doing things on the ocean. That's about 70% of the climate of the planet is covered by oceans, but it's something we don't think about enough. So I have two gentlemen here who both have some notions about a proposed method of improving the climate through something called ocean iron fertilization. People sometimes use other terminology because it's one of those things that people are trying to avoid using the term geoengineering, which puts people off. So they think up new terms, and I'm not even going to try to tell you what some of these alternative names are, but it may come up. You may discover that you've been reading about this all this time, but it was under a different name. Anyway, I presume in Boston or Cambridge is Jonathan Lauderdale, who is at least affiliated to MIT. I don't know where you're located today.
Yeah, sitting in Cambridge, Massachusetts.
Very good. I lived in Cambridge for a while. And it's very good to meet you, Jonathan, and to know that you're an oceanographer and that you do modeling, because that's certainly an important part of our effort to save climate. And so I want to have you've already met Peter Fikowski, who is almost regular on my show, because when I have a different topic about climate, I always think of calling Peter for advice or to participate, because he's willing and engaged and just all around nice guy. So hi, Peter.
Hi, Metta.
You're in California. You're in Silicon Valley, aren't you?
Yes, in Los Altos. Yeah.
What is this thing called ocean iron fertilization?
Well, ocean iron fertilization is a remarkable approach to working on the climate. And so we talked about Cambridge. I was an undergraduate there in the mid-'70s. And back then we heard about global warming. And I always figured this is a few years after the EPA was created in the US. And I thought, it's basically the atmosphere is going to be a big Superfund site, and EPA is going to get the excess CO2 out, just like the EPA and Superfund sites get the whatever chemicals out of the land. And as an astrophysicist, I decided that was far from my field of expertise. But
wait, hold on. That's interesting. I've never heard you claim to be an astrophysicist before, because I don't know what that is.
Well, I don't have an advanced degree. I decided after I have a bachelor's in physics, and I studied a supernova in a galaxy called M82 or M83. It's now been 50 years, and my brain slipped. But it's one of the nearby galaxies, and there was an amazing supernova there, and we were studying the chemistry that happened about 50 million light years away. It was interesting, but it gave me access to looking at at a physical entity like a galaxy or our planet, using the basic numbers.
Mm-hmm.
And is I got this many photons from hydrogen that was activated by this much energy. That doesn't mean that there's not other stuff.
Mm-hmm.
It just says you only have those data points, and it's turned out to be valuable in studying our planet. I spent 30 years as a volunteer working on hunger and poverty issues, doing advocacy in Washington to fund the projects that vaccinated all the world's kids. When we started, it was just North America and Europe, and then UNICEF said right at the end of the Apollo program, UNICEF sat up and said, you know what? It's time for us to make our moonshot, which is vaccinate all the world's kids. And we'll do that by 1990.
Mm-hmm.
my group, the group I was part of, got involved in the last 5 years when things were not looking good. And if you've ever done a project, you know, the end of the project is always when you realize things are really not looking good. So we got involved in the last 5 years, got the funds from Congress primarily, and finished the job. And so the world vaccination rate went from 8% to 85 and stayed 85 ever since 1990. And it changed the world. Right, the world
What rate?
from 8% to 85.
What rate? What is
Vaccination rate. The number of kids, percentage of kids who actually get vaccinated for diphtheria and the childhood diseases.
Okay, so you're one of the world savers. Okay.
That what we all want to do is fix the climate,
Mhm.
and that we hadn't had a definition of what it meant to fix the climate. You know, and so Meta, you and I are a little older than Jonathan by appearance. And we remember the moonshot program where Kennedy said, land him on the moon, bring him back safely by the end of the decade, boom. 8.5 years later, done. Because he had a very specific what by when goal. The vaccination was the same thing. Vaccinate all the world's kids by 1990. Now, 85 isn't all of the world's kids, but it still transformed the world. But it was a what by when, and then boom. And so coming into the climate, I had that background. So when it came time to climate, I and the people around me said, okay, good. What we really want is to restore a safe climate for our children. And how do you define that? And you know, there was a lot of debate. But ultimately, it was, I got this from, what's his name, who developed Drawdown, Hawken. It said, listen, the obvious answer is the highest level humans have ever survived. We want to be below that, because above that, we're playing Russian roulette with our kids. And we don't do that. And so no matter what the science says, we can look at the history. And that was the 300 parts per million. And so now we have this goal of getting CO2 back to where it was 100 years ago, and to do it while we still can. And the general consensus was by 2050, you know, just like any of these projects, you pick a date that sings to your heart, and that's the basis of 2050. But now we have, all of a sudden you can go boom, because you know how many gigatons per year you need to remove to achieve it. And then you can look at and we did this, and that's 60 gigatons per year, starting in 2030. So it gives over 20 years. And then we looked at what are the methods available that can do that. And it turns out that the only method that can do it is the method that nature uses before ice ages, which is ocean fertilization. And
that's
so
that's quite a long segue, but indeed, that's an interesting point, you're claiming that's how nature has done it before.
Yeah.
Okay.
Yeah. I know you can't prove it, but there's a lot of evidence for that. And there's no decent evidence for anything significant other than that.
Okay. Now explain what it is.
Yeah. So ocean fertilization is an answer to the question of why is most of the ocean blue when there's lots of water, lots of nutrients, and lots of sunlight? Why isn't it turned green just like the forest turned green? And the answer is, in most of the ocean where it's blue, is there's a missing micronutrient, which is iron. And iron doesn't dissolve well in water, it tends to sink. So that the only source of iron in most of the ocean is dust storms and volcanoes and whales bringing it up from the depths. And so iron fertilization is putting a little bit of iron in the right place at the right time and turning that part of the ocean green in such a way that when plants grow on land, of course, eventually they die and rot. In the ocean, when plants grow, they metaphorically, don't usually say this, but since Jonathan's here, I'll be a little more accurate. Metaphorically, they sink, and in the deep ocean, there's not enough oxygen for it to rot, and the carbon stays there. And that's how uh, that's how ice ages happen, is there's enough iron that gets distributed across the ocean, and the dissolved carbon compounds stay in the ocean, not on the ocean floor, but just dissolved in the ocean water, so that something happens, and it's not clear what, but at the end of an ice age, that dissolved carbon comes out as CO2 again, warming the planet back up. So the iron is used to get a lot of flora happening in the ocean. The CO2 is pulled from the air, sinks into the water, and stays there for thousands of years until something happens and it comes back up, released back into the air, warms the planet again. That's the end of an ice age. So,
okay, but now there are a couple of other claims that I've heard connected to ocean iron fertilization, things that link it to other technologies. That, for example, that these plants emit something with an acronym that I think starts with a D, that creates,
dimethyl sulfate.
okay, and that it whitens the clouds, and it what else does it do? Anyway, there are claims that it works in 3 different ways to help the climate. Can you explain those 3 different ways?
I can just do one, which is that there's a little bit of controversy about it. That is, it's very hard to prove, and I don't know why, but it is. But the dimethyl sulfate becomes a seed for clouds, and so you get more clouds, and the white clouds reflect more sunlight into the air. Jonathan, why don't you? I can see you can say if you add to that.
Yeah, that's my understanding of the effect of DMS.
Okay. And so
you both agree that this is something that happens, but the main thing is the main mechanism for cooling the climate would be the production of greater phytoplankton because of the iron in the water, and that would absorb CO2 from the atmosphere just the way plants do on land, and then either get eaten by fish, which would be very nice because we'd have more able to feed more people, but also some of it would simply sink to the bottom of the ocean, or at least some way down and not come back up for a while.
Exactly.
Yeah. And that way we remove the CO2 from the atmosphere, and for a long time. And now that's what I've heard people say, well, maybe not so long, or maybe get back in quicker than you think, or things like that. So let's see, you've given the best case. And unless you have something more to say, I'm going to ask Jonathan to see whether or not that is a plausible story, that he thinks really it would work that way, or would something go wrong, like
well, let me add one thing where I started, which is that when we look at the survival of our grandchildren, there's nothing else on the table that can remove the CO2 fast enough. The closest that you and I have discussed, Meta, of course, is synthetic limestone, but that's a lot more work, and it's going to take quite a few decades to get that scaled up. And so ocean fertilization is the kind of thing like it's our only way to do it, and so we should start quickly and find a way to optimize it. We know nature has done it. Nature has not done it as fast as we have, or as fast as we want to. But we have more engineers and scientists and computers than nature has by a large margin.
Okay, Jonathan, is he right, or do you have some caveats?
Yeah, I think that's in the ideal scenario, you would add iron that would generate a phytoplankton bloom that would take up CO2. The phytoplankton would either die and sink and be remineralized in the deep ocean, which locks carbon away for hundreds or thousands of years, depending on exactly how deep it gets. And yeah, so that's the ideal scenario. When we've tried ocean iron fertilization in the real ocean by experiments where you've gone out on big ships and dumped a bunch of iron into the ocean and tried to observe what happens, yes, you generate phytoplankton blooms, and some of those blooms are you can see them from space, which sizable effect. You can measure the change in CO2, so that's two checks. But I think after that, the ideal scenario breaks down somewhat in that the fate of the carbon after it's been drawn down is not so clear. So in some cases, maybe you do measure sinking particulate export using traps or other methods, geochemical methods that you can use from observations. Some have revealed that new biological material, organic matter, is reprocessed by zooplankton, so the tiny animals in the ocean, the grazers, and that allows the CO2 to reside in the upper ocean, which doesn't trap it for nearly as long as if it's exported to the deep ocean. So I think there's still
excuse me, but when it doesn't trap it as long, how long is it? Is it good enough to make it useful to us, or is it like 2 days or something?
Yeah, it depends exactly on what depth, but usually, like if it's within the sort of top 100 or so meters, you might expect that to be released back to the atmosphere within a year, due to winter storms that mix the upper ocean. And even at the base of that layer, a year is probably the longest you might expect, going down maybe to 10 years, something like that. Mm-hmm. So when we're talking about, trying to fix the climate by 2050, sort of CO2 sequestration at 10-year levels is not really going to make the grade. I think that so that's the observations. I think the models don't necessarily show either a climate scale drawdown of CO2 on the magnitude that's required, but also I don't think the models are there to be able to make those kind of predictions. So I think we need to do more process experiments where perhaps on a small scale you do iron fertilization experiments and then really measure every stage of that CO2 pathway from atmosphere to uptake to fixation and sinking and export and sequestration. And I think doing that in different regions of the ocean is also really important, because, for example, what happens in the Southern Ocean is not going to be the same as what happens in the tropical Pacific or the North Atlantic. So these are the kind of things that the experiments need to be done in the different regions, because the models are already integrating that whole system. So if you do an experiment in a model in the Southern Ocean, that integrates the entire globe response of the ocean ecosystem and the ocean carbon cycle.
Well, why would it not behave the same in different oceans?
So in different ocean regions, you have different nutrient requirements. So, for example, in the Southern Ocean is how Peter described it, where there's lots of nutrients, and for 6 months of the year, there's plenty of light, but there's not enough iron. So you can go to these regions and do these iron fertilization experiments, and this is where you generate generally the large blooms. And this high nutrient, low iron scenario also exists in the upwelling regions of the tropical Pacific and the North Pacific. So if you were to go there, you might get a similar response. It would be different because of different temperatures and other things, different ecosystem structures, stuff like that. On top of the same nutrient levels. If you go to the North Atlantic, for example, that is very close to a large source of iron from dust from the Sahara.
Yes.
And so that region has sufficient iron, but it is deficient in macronutrients such as nitrate and phosphate. And so if you go to those regions and add iron, nothing happens because they require other things. There's an open question about nitrogen fixation.
Question, is it nothing happens or not much happens?
Sorry, that's a good point. That's a good point. Probably not much happens.
Okay,
yeah.
Great. Okay, good story. Keep going.
Yeah, so you know, there's a question about nitrogen fixation where certain bacteria can use phosphate and iron. It has quite a high iron requirement, which is perfect in the North Atlantic, to create their own organic nitrate that they can use, or nitrogen that they can use. So not many other bugs can do that, which is why they depend on the dissolved nitrate in the seawater. So that's a bit of an open question. Yeah.
Now, I understand that there have been quite a few experiments of people actually trying this, and like 8 or 10 or something like that. I've just heard that there have been experiments, but I haven't heard how they turned out. What is is there a general consensus about what these studies have yielded in terms of what we know now because of the studies, or do they point in different directions?
So I think they agree in that adding iron, particularly in the Southern Ocean, generates phytoplankton blooms and does draw down the PCO2 in the seawater, which is one of the predictions of the theory. But I think the fate of the carbon after that is the open question. That those different studies have produced different results.
Well, would you say that? I mean, one of the very interesting side effects, and maybe it's worth doing it for that alone, is the increase in the fish population, because we've got 9 billion people going to be on this planet, and there's we're foreseeing problems about feeding the ones we have in the next few years because of climate change. So I don't know how we can increase it unless we do bring in things from the ocean. Now, could we increase the fish population by the phytoplankton? It is enough to make it worth doing.
I'm not an expert on that part of the story, but I think I would caution that I'm not entirely sure that you can have it both ways. You can have CO2 sequestration and increasing food stock, because if you're increasing the food stock, you're putting the carbon that you sequester from the atmosphere into the fish, and then you're eating the fish. And that means that the carbon that gets sequestered in the fish from the atmosphere is then going to be respired by humans. Yeah. And that puts the CO2 back into the atmosphere on a short time scale, which means that the net effect is to not reduce atmospheric CO2. So I'm not sure that you can have it both as a CO2 sequestration thing and solving the food crisis thing. I think there's a similar argument with the kelp reforestation idea, in that you grow a bunch of kelp and then sink it into the deep ocean. Well, you could also eat that kelp because it's very nutritious, and that would also help to feed the growing population. But that wouldn't also sequester CO2 for very long, because that CO2 would be respired by us living and growing and stuff like that.
Can I add something to that?
Yeah.
So I think another answer is yes, and. So you can design the kelp or the phytoplankton project to produce some amount of fish and some amount of carbon sequestration.
Yeah.
And right, because with in any economic system, you have sort of a point of diminishing returns. So it doesn't take that much fish to make a big difference, doesn't take that much CO2 to make a big difference. And so there's going to be a point where you say, you know what, this much fish, this much CO2 removal, and everyone's very happy.
I mean, that makes sense. Yeah, I just don't think you can have both doing everything. I think that's right. the point I was trying to make. But I don't think the models that you have to use to predict that would do a very good job either. So right. It's like a sort of the design of those systems would need to be very carefully assessed.
What's wrong with your models? You've sort of indicated that that's not adequate.
Yeah. So the models rely on both observations of the ocean and parameterizations of biological processes, basically turning the messy biology into a mathematical equation that you can then run on a computer. And those parameterizations, those equations, have parameters in them. And so sometimes it gets to a point where the parameters cannot be very well constrained by the observations, because there are not enough observations, or they're not the right kind of observations that you need to fit to constrain your parameters and stuff like that. So, we've been researching the iron cycle itself for 20, 30 odd years, something like that, and they're still developing. They're still including fundamental processes that we didn't know about before. So, for example, until about 10 years ago, something like that, we relied on models that just took into account of the cycling of iron, and that was very simple. So you'd have some dissolved iron, like Peter said, it's not very soluble, and it would be lost by scavenging, basically rusting or being absorbed onto these particles and sinking. And there was an input of dust. More recent models in the interim have introduced an additional parameter or additional thing that cycles with them called organic ligands. And those organic ligands help the iron remain available to the phytoplankton. And so those models then had a fixed concentration of that ligand, but we didn't really have enough observations to say how that ligand cycled. Over the last couple of years, maybe 5 years, 10 years, something like that, we've had a vast increase in the number of observations of both iron and ligand and other trace metals, thanks to a big project called GeoTraces, which has gone out and done sections across the ocean using these specialized techniques that you need to measure these things. Previously there weren't that many observations because it's really hard to measure iron, because you go out on a big rusty ship and you have metal equipment and stuff like that. So all your measurements would be really contaminated unless you had these really specialized techniques, these really clean instruments, and you sort of took into account of all these other things. So measuring iron is really, really hard, which is why there weren't many measurements. And there still aren't that many measurements of iron in the ocean. Modeling I've done and other people as well, but modeling that I've been particularly interested in is how do these organic ligands affect the concentration of iron? So there's an additional cycle that goes on top of the iron cycle, which helps keep the iron available. And so, you know, just making this parameter now variable can lead to some really unexpected and unusual behavior of the iron cycle. So
where do you get these ligands? Is it part of some sort of plant that you throw in with the iron, or what?
So ligands are like organic molecules that some bugs produce ligands to competitively trap iron. They're called siderophores. So they're produced by, like, you know, iron is scarce, and so some creatures have evolved to produce these things to make them more competitive, and to trap iron. Other things that help bind iron might be excreted from a phytoplankton, such as like sugars and stuff like that, proteins and what have you. And then also, when a cell dies, it has molecules in it like chlorophyll. Sorry, not chlorophyll. It has molecules in it that basically have iron bound to them when they're inside the cell. And when the cell dies and splits apart, those molecules can be released back into the ocean, and a tiny fraction of them survive and act as this stabilizing ligand now in the ocean. So you can have that as a constant in your model, or you can make it variable by linking it to biological activity. And we've only really just started, you know, investigating those things. And how
people gone out on boats with ligands and sprays them around?
Well, so I think they have inorganic ligands. So, for example, like water can act as a ligand, but not for iron because there's too much oxygen. But you can have other ions that help.
If I can take this a slightly different direction, that when it comes to solving the climate problem, which is what I think is bringing us together here, the question is, how do we discover how to do it? We know that our planet has ice ages. We know that this process happens. Well, we don't know. We won't know until we're done. But by far the best evidence is that this process happens. I'm told, anytime you put iron into ocean water, you get a fair amount of greening of it. The question is, how do you get that to turn into a reduction in atmospheric CO2? And then especially, how do you get that reduction in CO2 to last more than 10 years? Normally you would say 100 years, but I agree with Jonathan that if you've done 10 years, you're inches away from doing 100 years. So let's just look at 5 or 10 years. Because if you try to do research that takes 100 years to do, then we'll all be dead. So, an analogy is when Edison was figuring out the light bulb, he said that he went through 3,000 different formulations to find one that worked well, which was tungsten. And so the engineering approach needs to be done in parallel with the scientific approach. So Jonathan's talking about how do we improve our models so we can do better predictions and see places to do more interesting and valuable research. At the same time, we want to do sort of the Edison thing, which is, well, we know this thing works because we've seen it. And especially in 1992, after the Mount Pinatubo eruption, the CO2 data shows that nature somehow removed about 20 gigatons of CO2 in a year or so. And that's extraordinary. And so now that we know that it's possible, we want to, as quickly as we can, figure out how do we replicate that level of CO2 removal.
Okay, let me ask. I mean, I have heard that the Pinatubo effect was it's attributed to sulfur dioxide or something. but it's I've never heard anybody say that there was iron that does it emit a lot of iron that fell in the ocean and you had phytoplankton blooms too?
Yeah, there are two effects. One is the aerosols in the outer atmosphere, which reflected sunlight and cooled the planet by 0.5 degrees Celsius
Mhm.
For a year and a half, maybe two. And then separate from that was, as you said, the ash that fell into the South China Sea, a few hundred miles, a few hundred kilometers from the eruption. And that would have, while the aerosols cooled the air, cooled the planet, the ash would have incited the phytoplankton growth, which would have pulled CO2 out. Now, it could be something else, but no other theories actually add up to the numbers. So
I think that is also seen for more recent eruptions, such as the Icelandic eruption. I'm going to butcher the name, but Eyjafjallajökull or something like that. And I think
that's not the current one. That's a previous one, right?
No, it was a previous one. Yeah. That shut down European air travel for a while. Had produced a lot of ash, and that ash, I think, was iron rich. Went into a particular part of the Atlantic where the iron was a bit scarce, and I think that generated a bunch of phytoplankton. Also, the recent Hawaiian eruption.
That's right.
From 2017, I believe that generated some phytoplankton blooms off the south coast of the Big Island.
Yeah.
So I think these sort of natural iron pulses do tend to do at least that. Again, the fate of the carbon after that is hard to measure and not well known. But right. I still, I think there's also other iron sources, such as in the Southern Ocean, of the, you have a ripping current that runs around Antarctica, and that has several islands that are in the way, and some of them have iron-rich sediment, which can be entrained into the current and brought up to the surface, which also cause periodic iron fertilization driven phytoplankton blooms. So I think these are kind of natural phenomenon that do definitely have an effect in terms of phytoplankton. The CO2 drawdown is an interesting result.
I'd like to ask about the any overlap between these two different proposals for a climate repair, one being this iron salt aerosol thing and the ocean iron fertilization. But since both of them use iron, if I believe the iron salt aerosol idea is you fly around and sprinkle ferric oxide or something, some kind of iron into the atmosphere, which acts as a catalyst and knocks out the methane in the atmosphere. Well, now, when it's through, that iron's going to fall in the ocean, and would it have the same effect as the people who deliberately went out just to do the iron ocean fertilization?
Well, I've looked into that. The best answer I have is barely. That I don't think it would make a significant impact, because what we see with volcanoes is when I've looked at the CO2 levels over, for the Keeling curve, the CO2 since 1958, which has been carefully measured, that the only volcanoes I've seen that has impacted that was the Pinatubo. And then in 1963, there was a volcano in Bali. Now, the Bali volcano had about a quarter of the impact of Pinatubo, was still a huge impact. However, the Bali impact was only lasted less than a year, and then CO2 went back up to what what it would be if there had been no CO2 removal at all. And I find it, for me, that's fascinating because it tells me that one thing is growing the phytoplankton, but then the next thing is how do you get the carbon deep enough so it lasts more than 10 or 100 years? And as an engineer, we separate the two variables. First, let's grow a lot of phytoplankton, and then which is pretty much a solved problem. And then well, it's a solved problem at a low level, but then at the level we want for restoring the climate, that one hasn't been tested and refined. Then the next question is how do you get the CO2, the carbon sequestered? And when I look at the data, and this is the advantage of being an astrophysicist rather than an ocean physicist, I just look at the raw data and say, well, what's the difference between Pinatubo and the South China Sea and Indonesia, which is only, I don't know, 500 miles away. And the difference is the Indonesia is Bali is right almost on the equator where there are no eddies, no mesoscale eddies. And
No what?
big eddies in the ocean. They're called mesoscale, medium scale eddies, 100 to 300 kilometers in diameter.
Okay,
And it
I've
seems
heard about eddies, but I don't know why they're important.
they're important. They're probably important, so I say, and I think a number of people are beginning to agree, or tentatively agree, that when you get an eddy on the planet, if it's not on the equator and it's not at the pole, then the eddy is just the nature of centrifugal force on the rotation of our planet is going to cause the water to be pushed downwards or upwards. And so you have downwelling eddies that are clockwise in the northern hemisphere. And if it's a counterclockwise, you have upwelling. And it's easy to see on the maps because an upwelling eddy is cold in the middle because it's pulling cold water up. And then by comparison, a downwelling eddy is maybe a tiny bit warmer in the middle because it's presumably pulling the water down. So that's the hypothesis.
I've been aware that upwelling is very important, but I didn't know that it had anything to do with eddies. Okay, thank you. All right, I deflected you. Go back to
that's an important question. And so what I'm excited about this because we can incrementally, as I said, grow the phytoplankton, and then we can do tests to see what is it. Was it the downwelling eddy where the ash fell from Pinatubo that brought the carbon down? It's fascinating. There's one of the big questions, and I haven't had a chance to ask Jonathan. We can discuss it offline, but the 12 to 14 or even almost 2 years of carbon removal from the Pinatubo. It's like, how could that have happened? What would have maintained it for such a long time? Well, we'll have to find out. It happened. And in fact, in the Bali volcano, it was also more or less the same phenomenon that I wouldn't have expected it because we do have good measurements from the eruption in Tonga 2 years ago. In the winter of 2 years ago, there was this big underwater eruption, and the satellite measurements showed that the phytoplankton lasted 10 or 12 days, and then they dissipated into the noise. And so seeing this carbon removal that lasted 6 to 15 months, like, how did that happen? Well, the way you find out is you do testing. And so I'm excited to help get that testing started as soon as we can.
I think it's really interesting. Like the ocean is so variable. You look
Yes.
at a map. You look at a map of the ocean, and people draw these nice smooth arrows on them. But really, it's a real sort of chaotic kind of, there's eddies and all sorts of fronts, and it's so variable that 500 kilometers can make a huge difference. Even the timing can make a difference to the amount of or just to the effects of different perturbations. Yeah.
Yes.
And
So
then that's why the models need to capture these small scale features better, because at the moment the IPCC models, for example, have nominally 100-kilometer scales, and that is not sufficient to properly capture these mesoscale eddy features. You need a model that has 10-kilometer resolution or less, and that just increases the computational expense of those simulations by so much that they're not commonly done. But with advancements in GPUs and stuff like that, we can start to make a dent on getting that resolution down to the right level to capture that ocean variability in much better fidelity.
Yeah. And Meta, I think an important thing to see is, and for the audience, is there's the science of it, which is critically important, and then there's the engineering of it, which is separately critically important, because you want to keep refining the science, obviously, and you want to keep refining the data. What's nice about engineering is it's goal directed. In my career here in Silicon Valley, I've had the goal of increasing the efficiency of semiconductor manufacturing. And we don't want to go into those details, but I work with a factory. There's a certain process. How do we maximize that process? Very clear, and we get results, in months or a year. That's separate from the exploration in science, which is also critical, which is wide open. You say, give me any data you've got, and I'll add it into my model. And we want to do both.
Yeah. I want to ask about.
So sorry, can I just to add to that? I think they do converge at the point where the marine CDR community come into it, because CDR is carbon dioxide removal, because there's a big push for using models to validate the amount of carbon that is drawn down, and then assign carbon credit to that experiment. I think that's where the models and the observations link in with the engineering, when people start to want to make lots of money off of it.
Yeah, well, Jonathan, that's a really important point. And the hour is coming to an end here, and let's discuss it offline. But the pushback against that point, which is obvious, and there's no arguing with what you said, but the carbon offset model is so minuscule compared to the 50 or 60 gigatons a year that's needed, that what I found is it really, I hate to say it, detracts from those of us who want to actually restore safe CO2 levels, because what you can do with the carbon offset model is the wrong order. It's wrong by 3 orders of magnitude for the most part. They're trying to do maybe 1 billion tons of CO2. We need to do 1 trillion tons of CO2.
I want to switch to the question of how soon you could actually deploy a system like this. How quickly could you do something at scale if you decided that we wanted to, or get permission in a way? And the question of whether or not anybody is claiming they know of some risk involved. Is this considered a dangerous thing to do? For any reason that we actually understand now? Is there some side effect that might happen? what do people who argue against this have against the idea in particular?
Well, I've studied that a lot, and Jonathan, jump in whenever you can. But this has been most of what I've been doing the last 5 or 6 years, and there aren't any reports of dangerous phenomena from ocean fertilization. Doesn't mean it's not going to happen, but it's always important to look at the actual data. And nature's been doing it for at least 1,000,000 years and probably 1 billion years. And so we're confident that nature is well adapted to carbon removal because we've had ice ages. So the safety, it needs to be monitored, of course, just like anytime you're farming, you monitor for bad things that happen, even though people have been farming for thousands of years. So there's both sides of the safety. In terms of people's opposition, it comes right back to what Jonathan and I were saying a couple of minutes ago, that if your climate goal is to eliminate emissions, then removing CO2 is counter to that. Because if we fix the climate, if we restore a safe climate, then you can't pressure people who are driving their car or taking an airplane. If the climate is fine, how do you tell them to stop doing that? Now, when you think about it and you realize, oh, the purpose of climate work is to restore the climate and restore safe CO2 levels, then that's a whole different game. The environmental community is right in the middle of a shift from reducing emissions to producing a safe climate. Because back in the 1980s, they were the same thing. The climate was safe, and they said, let's see if we can keep the climate safe. But that changed in 1988 when CO2 went above the official 350 parts per million limit. But that was a long time ago, right? That's 37 years ago or something. And no one's changed we're just now changing the thinking that our goal is it's no longer appropriate to just focus on emissions. We don't have to focus on CO2 levels. And the opposition came from the fact that the ocean fertilization does not have any impact on emissions. And therefore they said it's a false climate solution. Mm-hmm. But I think that is changing this year. And so that's your second question, which is how, can it be done? We're working with some groups in the Philippines right now to get a project going in the same off of Mount Pinatubo to do a replication test and start doing that testing within 12 months. Whether we can do it, we shall see.
And you're going to have Pinatubo blow up on schedule for you. You're going to say now, 3, 2, 1, go.
Well, I'm gonna not say anything for a second, just so people's imagination can run wild for a second. Okay, the second's over. No, not that, but it's a funny story. No, we would distribute about 100 tons of iron fertilizer. So the same fertilizer you put on your yard or on a cornfield, iron sulfate. And it's about 100 tons. So it's about $100,000 worth over a 100-kilometer square area. So this is similar to a test that was done in 2012. Yeah. And but that was done in the Gulf of Alaska. This would be done in that downwelling eddy off of Pinatubo. And so we're hoping to get that started within a year.
Oh,
because there's really no reason we can't.
How would you expect any climate change? You couldn't expect that to have any observable effect on global temperature, would you?
In the first one, no. The first one, the scale is I don't have what fraction, but it's a fraction of what's needed. But as engineers, what we're doing is we're saying, okay, let's assume that it works as we expect it to. What would the next step and the next step and the next step? And so within 3 years, we can, if things go according to plan, and nothing goes according to plan, but you make plans in case they do. If things go according to plan, then in 3 years, then we could reach net zero again. How about that? And so
Uh,
then now you can see the issue is not so much the science and the engineering, and those have to be done, but it's like, oh my gosh, how do you arrange the global politics so that that shift from focus on emissions to focus on CO2
yeah.
levels happens rapidly. And that's right now where my group's attention primarily is,
Yeah,
while we're still
I
working on
wonder
it.
whether Jonathan would even be
Yeah.
in favor of having you do this.
I
Jonathan,
Yeah,
you
mean,
let's
think you
hear
I,
should
it.
go out there and do
yeah,
that?
I think it's a lofty target. But I still worry. I think we need to do more scale tests before deploying as a large scale solution. Just because we don't
Yeah.
understand the system well enough to be able to make predictions about a large scale tweak to the environment. I
But I
think,
totally agree. I totally
yeah,
agree.
yeah,
We'll
yeah.
say more in a second. Yeah.
So, so I think that the government permissions thing is uh, a hurdle that needs to be sort of worked on a bit to allow these smaller tests to occur so that we can learn more with our newer instruments and our better observing technology and stuff like that, and learn more
Mm.
about the ocean ion cycle and interactions with the ecosystem at a larger scale. And I think on a global scale, I do have reservations about ocean ion fertilization itself, in that I think that on timescales that are slightly longer than a human lifetime, the ocean is connected in a sort of global conveyor belt type situation where I think if you take nutrients from one spot, like the Southern Ocean, and you do it at scale, we're talking about large scale ocean ion fertilization here, in the future sometime, taking nutrients from one region, which is downstream of another region where the nutrients currently are used, leads to potentially unexpected side effects. And the way that you'd measure those things and observe them is difficult and unexpected, I think. So one scenario that I might imagine is that you take a bunch of nutrients from the Southern Ocean, which then affects your fish stocks, for example, in the North Atlantic. And by the time the fish stocks start seeing issues, it's difficult to connect it back to the ocean ion fertilization in the Southern Ocean. And this is large scale, longish time scales. But I think these connections in the ocean are really important things to consider. And again, this is where like the modeling comes in,
Right.
to be able to make predictions about those things. So I think as a method for climate restoration, I think as part of a package of different things, you talked about the artificial limestone and stuff like that, which I think is another sort of promising method. Again, that needs a lot of research to get it up to speed with ocean ion fertilization. But I think putting all your eggs in one basket, for example, is perhaps something that we need to consider
Right.
if that's a good thing or not.
Well, let me cover the number of the things you said. So the first one was scale up. And so in engineering, it's part of any engineering process is to scale up carefully. And so we would start out, as I said, doing the same thing that was done 12 years ago. And then, and in this case, our plan is to divide it into a 4x4 grid to 16 sections where we can try different formulations of iron oxide, iron sulfate, and concentrations and phosphorus and so on. And so we can start constraining the test. And then once we're getting reliable results, which should, given how rapidly the phytoplankton grow in the equatorial regions, could be very quick. Then we can expand it from 100 kilometers to 200 kilometers to 300 kilometers. If we can, at that point, it's not unreasonable to think that we could get the same amount of downwelling as Mount Pinatubo did. I don't know. There's a lot that will be learned, but Pinatubo did it without engineers, without scientists, without any technology. And so with our very rapid research now, it's not shocking if we were able to reproduce that after 2 or 3 years of scale up, at which point we're at net zero, and it's still only 0.1% of the ocean area. And so now the thing, Meta, that's hope that's likely giving Jonathan a bit of a headache at the moment. Am I saying that is for 30 years, the oceanographers have studied the Southern Ocean, and just what actually is happening in the Southern Ocean is slow enough that the thinking is we need to do this to large fractions of the ocean basin. Now, I'm saying, well, let's be optimistic and let's notice that we have this data from Pinatubo, which says that we can produce the result, and we know that there's enough sunlight. There's, physically it's possible that we can do it in 1% or even a fraction of a percent of the ocean area if we replicate what happened in Pinatubo. Now, there may be some reason we can't, but the only way we'll find that reason is by assuming that we can, and then discovering that where we failed.
I'm all for being optimistic.
Yeah.
Let's end there. I want to be optimistic too. Go ahead.
Sorry, I just wanted to add one more thing, which was that you pointed out previously that Pinatubo potentially didn't just add iron, and that you potentially add other nutrients that the phytoplankton need. And I think that is a key thing that maybe affected the CO2 drawdown, is that it's not just iron. You're adding these other nutrients that the phytoplankton need, and that allows you to increase the amount of CO2 that you draw down over just what's in the ocean at the time. I think that's potentially a key part there. So just adding the iron, I think maybe that's not necessarily like the key driver. I think it's the coupling. If there's anything I've learned from working on oceanography over the last sort of 15 years, it's that these connections are really important. Like individual processes can do stuff, but I think the synergy of different processes is what really leads to significant changes. So.
That's great.
Okay.
Meta, let me just thank you. This conversation has never been had before, Meta.
Okay.
This is the first time this conversation, I've been talking to a lot of people, and you're getting us together is a watershed. It's a landmark moment. So thank you.
Well, it's always fun. It's my favorite hobby. And you guys are my craft tools. Anyway, I thank you very much. And we are over, so I better call this to a halt. But maybe we should get, there are going to be other conversations about ocean iron fertilization. So let's see how we can hook it all together and make a coherent discussion when other people join as well. Okay?
Yeah.
So this is terrific. I've enjoyed it very much, and I think it's important. I'm glad to know that you think so too. Okay.
Yes.
Blessings. Take care.
Okay.
Bye.
Thank you.
Thank you very much.
Bye. Project Save the World produces these forums. This is episode 607. You watch them or listen to them as audio podcasts on our website, tosavetheworld.ca. People share information there about 6 global issues, and we welcome your comments too. To find a particular talk show, check the scroll list on the homepage or use the search bar. Project Save the World also produces a quarterly online publication, Peace Magazine. which now serves as a free of charge newsletter to help mobilize knowledge about 6 global threats to humankind. We gladly email the magazine as a PDF or link to any interested organization in the world that works to prevent a global catastrophe involving war and weapons, global warming, famine, pandemics, radioactive contamination, or cyber risks. Just email us at office@peacemagazine.org and we'll add your group's email address without charge to our list. Please type "Subscribe my group" as the subject of your email. For individual subscriptions at $20 Canadian per year, go to pressreader.com on your browser and search for Peace Magazine.